Welcome to the final chapter for our statistics class, chapter 11. And there's two things in chapter 11, the goodness of fit and contingency tables sections. And that's it. It's not like there's a bunch of other sections that we're skipping or not going to get to. There's just these two. And we're going to do them both. And we're going to begin at the beginning by looking at a goodness of fit topic. So what is the key concept for a goodness of fit? By goodness of fit, we mean that sample data consisting of observed frequency counts arranged in a single row or column called a one-way frequency table agree with some particular distribution, such as a normal or uniform distribution that's being considered. We will use a hypothesis test for the claim that the observed frequency counts agree with the claimed distribution. So what does that mean? Let's again try to put a simple example out there to help us think about it. So they're saying we're going to have observed frequency counts arranged in a single row or column. So let's say I was, let's start real simple. Let's say I'm looking at cars in a parking lot, maybe for all the people that drive to DVC. And in my sample of cars in a parking lot, I make an observation of two things. And what we're going to do is we're going to say, I just looked at whether cars were convertible or not. So I'm going to put here convertible, and then it's simply going to be over here, then maybe not convertible. And so then what would an observed frequency count look like? When I looked at the bunch of cars, how many were convertibles? So let's say I looked at a bunch of cars and 60 of them were convertibles and 125 were not. So in this simple example, I have convertibles versus not convertibles. And we can see there was a total of the number of cars that I observed is 185. All right, so it says we want to see if the observed frequency counts agree with some particular distribution that's being considered. So, for example, maybe I had some expectation of how many people who drive to DVC drive convertibles. And so maybe I thought in particular that I would have some expected amount. So what I'm going to do is on the top row, we have the observed values. And then I could say what I expected to occur. And so there was this thing we did back in probability chapter 4 called expected value. So for example, if I think in the total population out there that I'm going to say that 25% of the DVC people who come to campus in a car drive convertibles. So then I expected that 25% would have been convertibles and the other 75% would have not been convertibles. And so those expected percentages or portions of the overall population, when I then look at the total of 185, would lead to some expected values. So if 25% were convertibles, then my best guess or the expected number out of 185 people drawing to campus that I randomly look at would be that 25% of those would have been convertibles. So what is 25% of? That's like 45, 46. So that would have suggested that if that were the case, that would have led me to think that about 46 of my 185 should have been convertibles. And then the other 139, I think it is, would have been not. And so by having expected values, an expected distribution, and an observed actual distribution from a sample, we can compare those and try to see if the expected percentages fit well with the observed percentages, with the observed values. The expected results fit well. So we can basically ask ourselves, is this a good fit? And when I say this, I mean my expected distribution. Does the expected distribution fit well with the observed distribution? And again, we never would assume that it should come out exactly right because there's randomness involved, but is it fit close enough for us to think that, yeah, this looks like this is a good fit? Or do we think that there's such a big difference between what we observed compared to what we expected that it's not a good fit? This is the big idea of a goodness of fit test with this kind of silly, simple example. All right, so this is the kind of thing we're talking about. So let's move forward. So we're going to want to have a hypothesis test for this. A goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. So in this case, I could make a hypothesis test that the observed distribution of convertibles to non-convertibles fits with my expected 25% convertible, 75% not convertible distribution. This is what I think the population has, and then I take some observations and see if it fits with my expectations. So our objective is to conduct a goodness of fit test, which is a hypothesis test to determine whether a single row or column of frequency counts agree with some specific distribution. And they say, well, it could be maybe your specific distributions you're trying to check at are a uniform distribution, where all the categories are evenly distributed amongst the population, or even a normal distribution. We could sort of say, we think this looks like the population is normally distributed. Let's fit that. In the past, we used a normal quantile plot as a way to check to see from a sample whether we believed that the sample came from a normally distributed population. Another way to do that is to use a goodness of fit test and say, all right, if we believe that the population is normally distributed, then we would expect observations to come out with sort of a normal distribution. Well, let's compare those expected observations with the ones we got and see if that's a good fit. See if it looks like the observed results would have come from a population that is normally distributed. All right, so here's a bunch of letters, and we want to know some of these and get the idea a little bit, but again, we are going to de-emphasize formula calculations and use instead technology to help us with the number crunching, but we do want to understand a little bit what's going on and also to be able to refer to some of the variables involved. So we have O is the observed frequency of an outcome found from the sample data. So one particular observed frequency would mean like usually in one of those cells in my little table. So if I go back to my starting table, like the 60 or the 125, those are each examples of an O. So it's kind of like an X value is a sample value from before. Well, now an O value is an observed frequency value from a sample. E represents the expected frequency of an outcome found by assuming the distribution is as claimed. So in this case from my table, the 46 and the 39, those are E's. And so we are going to compare the O's that were observed to the E's that were expected, right? They're trying to help make it easier for us by using these letters, O's versus E's. And then basically we're going to look at all of those differences and see if they seem to differ enough for us to say that that couldn't have happened by random chance. We may recall when we're looking at a bunch of differences, like the difference between data values from the mean, things like that, that we end up doing a bunch of squares. So you may be able to guess in advance that this is a chi-squared distribution. How far away is this from what we expected? K represents the number of different categories or cells. So in my little example, there was only 2 categories, convertible or not convertible. So K would have been 2 in my sample. N represents the total number of trials, the total number of observed sample values. That was 185 in my silly little example. And P represents the probability that a sample value falls within a particular category. So we had 2 P's in my example, the 25% and the 75%. So that was the probability of falling in a particular category based on expectation. So we'll hopefully warm up to these letters a little bit. As with all of our distribution analysis, we have some requirements that need to be met before the math makes sense, before the formulas can be relied upon and the results can be based on sound math. The data have been randomly selected. As usual, we need to do things randomly. Bad data is bad results. The sample data consist of frequency counts for each of the different categories. That's just because in a goodness of fit, that's the structure that we're working with. So the data values themselves will be how many in this category, how many in this category. In my case, there was only 2. There could be more. There could be 10 categories. For each category, the expected frequency is at least 5. So we had this happen before. We need to have at least 5 for there to be enough data values for us to make predictions to see if each category has been properly accounted for. So it says the expected frequency, not necessarily the observed frequency, but the expected frequency. There's no requirement that the observed frequency for each category must be at least 5. Because of course it might be that you mistakenly think that there's a category there that's represented and it's not, and your observations are the way to see that. But if you thought it would be, you have to have enough people in your sample so that the level that you thought you'd see it at would have to reach to at least, that you thought you'd see at least 5. And then maybe the observations will turn out to be different. All right, so let's get toward the test a little bit here. Again, the null hypothesis will always have to do with equality. So in this case, that translates to the frequency counts agree with the claimed distribution. Again, it doesn't have to be exactly equal, but the idea is if it's not very far from equal, then you can't reject the idea that they could be equal. And so we're going to have the null hypothesis that the distributed frequencies agree with or are equal to the expected frequencies. And then the alternative to that would be that they don't agree, that they're so far enough different, so far not equal away from what we expected to see that it's hard to contribute that to chance, and that the claim is that the expected distribution is not actually valid. All right, so having said that, we have these formulas that we hope not to have to use because we're going to use technology instead. Give me just 1 second. Sorry about the interruption. Okay, so when we're doing a test for the goodness of fit, as you can at least see from this diagram of the formula, it is a chi-square distribution. And as it has been in all of the chi-square distributions, we basically look at the difference between the observed values and the expected values. We square all of those differences and then average them out and add all that up, etc. But nonetheless, we're going to be able to produce p-values as usual or critical values. And there is I think critical value charts that are typically used when we're doing the critical value approach, but the p-value is the most intuitive and straightforward. So we'll use that whenever possible. So how would we find the expected frequencies? So in my simple example, I sort of just showed you if you if you already have some idea of how things will be distributed as a percentage or something like that, then you would multiply that percentage times the total that you observe to see how many of those observations would fall in a particular category by what percentage you expected to see there. So they crunched through some numbers to do this, but they can see if the expected frequencies are all equal, well, then you would expect each category would have an equal portion of all of the observed values. So they take the observed value number and they divide it by the number of categories, because they're saying they would be equally distributed amongst them, then that would be the expected observed amount. So if I had 4 categories and I made 100 observations, well, if I thought that they would be equally distributed or a uniform distribution, then those 100, I would expect to see 25 in each of my 4 categories, because that would be 100 divided by 4 categories. Now, if the expected frequencies are not all equal, like 25% for convertibles, 75% for non-convertibles, then you would calculate each E by multiplying the total number of observations times the percentage expected in that category. So I did 25% times 185 for my first expected value and 75% times 185 for my second expected value. So they're showing you a little bit of the nitty-gritty here. And it is helpful to at least understand how expected values are achieved. All right, so let's look at this example. There's a couple slides to illustrate this example. A single die is rolled 45 times with the following results. Assuming that the die is fair and all outcomes are equally likely, find the expected frequency for each empty cell. So here they have the observations in row 1, and then below it you would say, well, how many would I expect to see would be a 1, 2, 3, 4, 5, or 6 if they were equally likely, if it was a fair die? Well, since they rolled 45 times, you can't divide that evenly by 6. But again, for an expected value doesn't mean you actually expect to get exactly that value. The expected value defined in chapter 4 was if we did this experiment a bunch of times, on average, how many would fall into this category. And so on average, if these were divided evenly, then I would expect that 7.5 of the 45 on average would be how many I'd get in each box, because they're equally likely, so they would be equally distributed. On an individual trial, of course, I can't have any of these numbers be 7.5 because I can't roll a 6 7.5 times. But I would think that that's the average. Like sometimes you get 8, sometimes you get 7. It would average out to 7.5, but then in general, you'll be close to what's expected. So then if we have those expected values, we could try to make a comparison and see, well, if that was the actual expected distribution, if this really is a fair die, then what's the p-value? What is the probability that the results that I observed would come out the way they did if it was just by random chance? If everything was done randomly and there really is an even distribution because it's a fair die, well, they're not going to all come out perfectly the same, but it'd be harder and less likely to get extreme differences. So for example, we can kind of see here, like the 1 and the 3 showed up a lot of times and the 5 or the 6 showed up very few. Well, again, that could have just happened randomly. But based on how many trials we did, based on rolling 45 times, what is the probability that if this really was a fair die, I could get this extreme of a difference? That will be the p-value that we calculate. And if the p is low, meaning if that's very uncommon and very rare, well, then we'd say this gives us evidence to believe that the die is actually not fair, that these different results are not all equally likely, that somehow it's weighted maybe in favor of the 1 and the 3 or something, I don't know. But if this could occur by chance 20 or 30% of the time, then you say, yeah, it probably just happened by chance. It's probably a fair die. And that would mean a higher p-value would mean you failed to reject the null that this expected frequency could be exactly what's going on. Whereas if the low is null, if the p is low, the null must go, then we reject the idea that these are equally likely and instead say this provides evidence and support that these are not equally likely because this is not a fair die. All right, so this example, they were just in these first two slides, I think, focusing on the idea of seeing how to get expected frequencies and to understand what that means in this simple example of being equally likely. So not equally likely, so this was an equally likely example. In the not equally likely example, using the same results from part A, suppose that we claim instead of being fair that the die is loaded, so that the outcome of a 1 occurs 50% of the time, and the other 5 outcomes only occur the other 10% of the time each. The probabilities are listed in the second row. So now they've said, here's what we expect. We don't expect each one is going to happen 1/6 of the time. We're thinking the one's going to happen 50% and the other only going to happen 10% each. Then we could compare those with the observed values by creating expected frequencies by saying, all right, I did 45 times. So if half of them were a 1, that would be half of 45 or 22.5, matches with 50%. And then all of the others being 10% each, 10% of 45 is 4.5. So if the probabilities were as outlined, 50% for one and 10% for all the others, then these are the expected values we would get. And now let's compare those with the observed values and see if this seems like a good fit for the distribution. Again, we're assuming these were thrown randomly, so I don't think even if this is perfectly correct, 50%, 10% for each of the others, that it would come out exactly right. But maybe this is a much better fit and a more likely probability distribution for what's going on with the die. So in this case, they're showing you the way you would get each of those expected frequencies is by multiplying the probability that that result would occur times how many times you made observations and see how many you expected to get in each category. Okay. So now, in each of those cases, we had an idea of testing the die, or we have an idea of testing my theory about how many convertible drivers there are. So we can talk about measuring the disagreement with what we expected. And this is going to form a chi-squared distribution where you would crunch basically this chi-squared score by sort of measuring overall how far the expected values were from what we were thinking we would, what we actually observed, what we expected to get versus what we actually got. And so keep in mind, chi-squared is like an absolute value. It's never negative. It's just like how far away are the values we saw from what we thought we would see. And so it's a sort of a one-tail distribution. It's always a right-tail distribution. It's always, is it far enough for you to think that's unlikely or not that far? How much bigger than 0 is our chi-squared score? And as they kind of point out in the comparison, large chi-squared values mean a small p-value. The greater it is away from what you observed, from what you expected, the less likely that that happened by chance. So as the chi-squared score gets larger, the p-value gets smaller. And if it gets low enough to go below the significance level, we reject the low. If the p is low, the null must go. Whereas if there isn't that much of a difference, if the chi-squared score comes out kind of small, well, then the p-value will become larger because there's a greater probability, if not much of a difference is observed, that whatever difference you did see could have just occurred by chance. If it's not that extreme of a difference, then it might have just happened by random chance. The probability of that being true will grow larger, and that will mean there's a higher p-value. And if it goes above the significance level, then we fail to reject the null. And failing to reject the null means there's a good fit with the assumed distribution because there's not too much of a difference to be too rare or unlikely. Whereas a very big difference that would be very unlikely to occur by chance suggests that this is not a good fit with the assumed distribution, because we reject the null that their assumed distribution is equal to what was observed. So this little slide may help to sort of think about the logical pathways that we're going down. So let's take a look at this example here. 11 slides for this. So now they're actually kind of going to go through the idea of the test, and we'll skip slides where they're just showing us a bunch of formula use and see if we can save some time to hop over and do a homework problem after this introduction. A random sample of 100 weights of Californians is obtained, and the last digits of those weights are summarized in the table. The last digits of weights, based on the data from the California Department of Public Health. When obtaining weights of subjects, it's extremely important to actually measure their weights instead of asking them to report their weights, which we discussed a little bit back in chapter 1. Test the claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. So they're not being perfectly clear on this slide, so let's at least understand the idea of what's being discussed here. So let's say somebody reports a whole bunch of weights, of people's weights, and someone says, you obtained these weights by measuring them or by just asking them? And the person's like, oh, yeah, we measured every one of them, and you think they're lying. Well, one of the reasons we want to measure instead of just ask people is because people don't often have a good idea of how much they weigh. So that leads for much less accurate results that are hard to rely on. And also, they have a natural tendency to just round off to simple numbers. And so one of the ways that could be seen in the data, if you suspected that, is that when people round off, they'll often round off to the nearest 0 in their weight, or maybe the nearest 5. Like, yeah, I weigh about 155. I weigh about 160, whatever. So if you collected a bunch of weights by just letting people just guess at how much they weigh, you would probably get a lot more of those numbers that ended in a 0 or a 5. Whereas if you actually measured people, you would expect that the last digit of their weight would be equally distributed, because there's no reason, as somebody fluctuates in their weight through a whole variety of chaotic things, diet, exercise, all those things, to expect that they're naturally going to land more on weight values that ended in a 0 or a 1 or a 2 or anything else. You would think that those final digits in their weights are equally distributed. Now, maybe the other tens digits or hundreds digits might depend a lot more on the society and all these other things, but the last digit, those you would expect to be somewhat equally distributed. So that's the idea, the insight behind this. And if we just look at these examples here, the last digit ending in a 0 was in 46 of the data. The last digit ending in a 5 was in 30 of the data, and nothing else was above a single digit. So I'm guessing, just from a very stark example here, that they're going to conclude that these do not fit well with a uniform distribution, which would mean that not all of the last digits were equally likely, which means they probably didn't weigh these people. They let them just say how much they weigh. But nonetheless, so we are testing the claim that the sample is from a population of weights in which the last digits do not occur with the same frequency. So how do we go through the process as we were just showing? First, there's the requirement checks. The data comes from randomly selected subjects. That's been stated. The data do consist of frequency counts. They're showing how many times each of those last digits was tallied. And there's 100 sample values and 10 categories that are claimed to be equally likely. That's our claimed distribution. Each expected frequency is 10. So each, again, you would take the total number dividing by how many categories when you're assuming that they're equally likely is your distribution you're checking. So the expected frequency does satisfy the minimum requirements of being at least 5 in each category. Again, the expected frequencies have to be at least 5, not what you observed. And that's good because in our case, some of the ones observed were 0, or 7 was 0, and many were below 5. But the expected values were at least 5. All right, so our math should work then. The original claim that the digits do not occur with the same frequency, that's the original claim. That is, at least one of the probabilities is different from the others. So equally likely means everyone has the same frequency. And that is not true if any one of those does not match the others. If any one of them is more likely than the others. Like in the rolling the die, 50% chance of getting ones, the others were equally likely, but the one really stood out. That's not equally likely outcomes. If the original claim is false, then all of the probabilities are the same. They'd all be 10% in this case. So our null hypothesis is always about equality. In this case, it's counter to our claim because we're claiming that they're not equal, but the null hypothesis is always about equality. So they set up the null hypothesis, which is that all the probabilities are equal to each other. And that's a uniform distribution. And then the alternate hypothesis is that at least one of them is different from the others. So this is the general structure from a structure for a goodness of fit test. That basically the null hypothesis is that every category's expected values is equal to what you would observe, and that the alternate is always that at least one of them was not equal to what you expected. And in this case, we expect them all to be equal to each other, so that's what's written. But if it was testing against a particular distribution like normal or something else, or my expected 75% non-convertible, 25% convertible, then I could list the p-values and say that each one should be equal to what I'm thinking. P sub category, P sub 0 or P sub 1 for my convertible category is 25%. P sub 2 for my second category is 75%. Either way, whether you expect them all to be the same or you're going to specify what you expect each one to be, the null hypothesis will always be that it's equal to what you expected. And the alternative will always be that at least one is not equal to what you expected. Just has to be one to ruin it for the rest. It's that weighted one on the 6-sided die that makes it not a fair die. It points out no significance level was specified, so they'll select the most common choice of 5% to run our test. All right, so now we can perform the test. Because we are testing a claim about the distribution of the last digits being a uniform distribution, we use the goodness of fit test described in this section. The chi-square distribution is used. The observed frequencies are in the table. So here's the last digits are given, and those are the categories, and the observed frequencies are here. And that's the second column of the table. And so they're showing Excel stat, but we could basically put this table into StatCrunch, and it would give us p-value, chi-squared value, the test statistic, things like that, as we're seeing here. Each corresponding expected frequency is equal to 10. Now, they're not listing that here, but it could be shown. StatCrunch will just do all that for you. You don't have to do that unless the problem asks for that independently. So in this case, they used an Excel add and Excel stat to obtain the results. So they have a chi-squared observed value. So that's the test statistic. They have a critical value, which is the value you would need the chi-squared score to be in order to beat your 5% significance level. And that we can do that here. Excel stat gives us that all in one table. In StatCrunch, we have to do that in the chi-squared calculator, or sometimes they'll, in the problem, just give you the table of values for the chi-squared critical values, and you can just look it up on the table. Degrees of freedom is 9. So notice the degrees of freedom is 1 less than the number of categories. There are 10 possible categories, 0 through 9, and then you subtract 1 from the number of categories to get the degrees of freedom. And then they give you this little teeny p-value. And as I was pointing out, it's hard to believe if these were equally likely that you'd get 46 zeros and 35s and all the others would be in single digits. So the p-value is almost nothing. So they're showing some formula use. They're showing the expected values. As I said before, we are going to try to avoid doing most of this, but it is helpful sometimes to look at what's going on and to try to understand. The key thing is that these are the two things being compared. What we observed with what we would expect if the expected distribution were in place, which in our case we're testing equally likely. So the solution, the test statistic, this huge chi-squared number, wow, over 200. The critical value was, you had to be more than 16.9 and you were over 200. Or with an alpha value of 5, we would compare the p-value. P-value, it only goes down to the fourth digit, so it always says less than 1 in the fourth decimal place, but it was probably way less than that. But it's below the p-value. So they're reminding us that if you're using the critical value method, you see where you need to be. This is where you need to be at the 5% place, to be at the significance level. And the test statistic was way over here somewhere. So it was in the critical region above 16.9, meaning that you would reject the null hypothesis. If it instead wasn't in the critical region and was somehow below the critical value, then you would fail to reject. And so they're reminding you that you draw the conclusion based on where it lands up here. And in this case, they land in the reject the null hypothesis side because the value is way to the right of the critical value. Now, of course, we would have just compared the p-value to the significance level and say the p is low, so the null must go. As it states here, if we use the p-value method, the p is low, the null must go. If we use the critical value method, the test statistic was well beyond the critical value needed. Either way, the conclusion is there's sufficient evidence to support the claim that the last digits do not occur with the same relative frequency. We reject the null hypothesis, which is that they were equally likely, and instead, no, they did not look like they were equally likely. So that's the interpretation. The goodness of fit test suggests the last digits do not provide a good fit with the claimed uniform distribution of equally likely. Instead, it looks like actually weighing the subjects, it appears that the subjects reported their weights. In fact, the weights are from the California Health Interview Survey, and the title of the survey indicates that subjects were interviewed, not measured. Because those weights are reported, the reliability of the data is very questionable. Okay, so I'm looking at lucky number 7 from our final homework set for the semester. It says a police department released the numbers of calls for the different days of the week during the month of October. As shown in the table to the right, well, it looks like it's below to me, use a 1% significance level to test the claim that the different days of the week have the same frequencies of police calls. And then there's a follow-up. What is the fundamental error with this analysis? So if you take a bunch of calls from a month of October and you just show how many occurred on each day here, then we could test the claim that they're equally likely to occur on one day versus the other. So before we do any crunching and StatCrunch or anything like that, we can look to see how to set up the null and alternative hypotheses. Null hypothesis, at least 2 days have a difference. So the null hypothesis is always about the observed values being equal to what you expected. And the statement in our claim in this case is that we expect them to be all equal to each other. So that should be the null hypothesis. Police calls occur with all different. No, at least one day was different. No, police calls occurs with the same frequency on the different days of the week. So that's our null hypothesis. So then the alternative to that was that any one of those days is not in line with that. At least 2 days? No, any one of them is going to be a problem. Police calls occur with all different. No, they don't need to all be different. Just any one of them needs to be a problem. At least one day has a different frequency. That's the one we want. It might be more, but that's not a requirement for them to not be equally likely. Now they want the test statistic. So I'm going to take this and open the data in StatCrunch. Let's see what it looks like when we pop over this frequency table. And what we can see in StatCrunch is we get a column with the labels of the categories, which are days of the week in this case. And it says up top day. And then we get the frequencies observed for each of those days here. So to perform a chi-square distribution for a goodness of fit test, I'm going to go into stat, and we can see there's a choice for goodness of fit, and there's a chi-square test. So this is a goodness of fit to see if our observed values fit well with the expected values of being equally likely. And we're performing a chi-square test. You can even see the little x squared in the problem. So I go to stat goodness of fit chi-square test. So then the tool asks us to say which of the columns show the observed values. So that's this column here that says frequency. So I would choose that. And then which column shows the expected values. We could select a column. And we don't have a column for that. But one of the other choices here is all cells in equal proportion. So if you're just testing to see if they're equally likely, that can just be done automatically. If we're not testing that they're equally likely, then we would have needed something that shows like 25%, 75%, or in my first example, or the 50%, 10%, 10%, 10% for the loaded die. You need to have something to say what you expected. But if we're just trying to see if they're all equally likely, that's an automatic choice here in StatCrunch to make our life easier. So then I compute. Now, the nice thing is when I do that computation, it does show us what the expected values would be as well. It makes that column for us so we can see, and then we can sort of imagine, are these different from that very much or not? But we do have a p-value here. We do have a test statistic. We have degrees of freedom. There were 7 days of the week, so degrees of freedom is 6. There was almost 1,500 observed values in these added up, totaled up in these frequencies. All right, so first they want the test statistic, which is the chi-square value, to 3 decimal places, which means I have to round up that ending 4 to a 5. Then p-value, it's gonna, let's just try putting in a 0 because it says less than 1 in the 4th decimal place. So then we draw a conclusion, and the p is low, the null must go. The null is that these are equally distributed. So we think there's evidence that they are not equally distributed. So we reject the null. That's either A or C. There's insufficient. No, if you reject the null, it's because there was sufficient evidence. I don't need to read anymore. It's got to be C. Now they do ask us to draw a final conclusion in this problem, unique to this problem and its circumstances. And so you can think about it a little bit, but let me just point it out to you. If you are trying to see if days of the week are equally likely, well, when you're taking your sample, you should have each of those days equally represented. You should have a whole number of weeks. So the fact that they did this during the month of October, which has 31 days, well, after first 4 weeks of October, 28 days in, you had 4 Mondays, Tuesdays, Wednesdays, Thursdays. Each of the days of the week showed up 4 times. But then for the next 3 days, the next 3 days of the week got an extra boost added to their totals because they got counted a 5th time in that month. So that's what they're going to talk about here. And then all of them say because October has 31 days, but then it has 1, 3, each day occurs the same 2. So I would say 3 of the days of the week occur more often than the other days with 31 days. That's a fundamental error by taking 1 month instead of taking a set number of weeks. All right, so the next one is somewhat similar. It says the table below lists the frequency wins for different post positions in a horse race. So this was the post position, and this is whether they won or not. And it points out that the post position 1 is closest to the rail, so that horse might have a little less distance to run. Maybe that gives them a hedge up. and helps them beat somebody who's a little better than them. So we're going to test whether the position you were put in at the post of the race is all equally likely to still win the race, or whether we think maybe if you're in first place, you win more often because that's a better place. That would make them not equally likely. So as in the last problem, the null hypothesis is that wins occur with equal frequency in the different post positions. And then at least one position has a different frequency would mean that that's not true. And they want that test statistic. So I'm going to open the data in StatCrunch. Again, we have our two columns here, and I'm going to go to Stat, Goodness of Fit, chi-squared distribution. I'm going to select the frequency of the observed values, which were the wins, and see if these are all equally likely and compute. And it shows us if they were equally likely, on average, we would expect that 11.6, since 116 were observed and there was 10 different possibilities, then 11.6. And so there do seem to be some differences, but let's see if it's enough to warrant the claim that we think these are not equally likely. First of all, the test statistic to 3 decimal places. 17 is a pretty decent sized chi-squared score. The p-value is pretty low. They want that to 4, which is what we're given in StatCrunch, so that's convenient. Now I think we need to draw conclusions. So what was our significance level? Our significance level was 5%, and our p-value is less than 4%. If the p is low, the null must go, so we reject the null. That's A and C. C says there's sufficient evidence. Based on the results, should bettors, I guess, consider the pole position of the horse race? Well, it sounds like they're not equally likely, so that has something to do with their likelihood of succeeding. So I'd say, yeah, you should consider that.